So we have two tasks to get to today. We're going to talk about something called entropy and something called free energy, and you might want to get a calculator handy for what we're doing today. So our objectives, first we're going to know the difference between an increase and a decrease in something called entropy. We haven't defined that yet. And we're also going to define something called free energy and know that it takes both enthalpy and entropy into account. Basically tells us whether or not a reaction is going to happen or not. Also, we're going to differentiate between spontaneous and non-spontaneous processes. Again, that tells us whether or not a reaction is going to happen. The vocabulary, we're going to see spontaneous reaction. Again, that's a reaction that happens on its own with no outside intervention. Entropy is a measure of the disorder or chaos or dispersion in a system. The law of disorder basically says that entropy is always increasing. And we're going to talk about this thing called free energy. So entropy, look at these pictures and think about which one looks more like your room, okay? This one down here might look like your room on Monday, and this one up here might look like your room on Friday. And so that's actually the law of disorder or the law of entropy, okay? The law basically says that entropy is always increasing. So entropy, which we abbreviate with a capital S, is our key word here, and it's the randomness, the disorder, the chaos, the dispersion of stuff. Okay, so this nice pink room down here in the corner has a very low entropy, okay, so low S, and this one up here has a very high entropy value, okay. The universe wants more entropy. It doesn't want anything really, but the universe tends toward more entropy, so entropy is usually increasing, okay. Chemical reactions that increase entropy are usually more likely to occur than ones in which entropy decreases. So if you think about it, again, this is what your room usually looks like on Monday, and through no fault of your own, through no effort, it ends up looking like this on Friday, okay? And if your mom ever, bugs you about, why did your room get so messy? Just say, well, it's a law of the universe. Entropy tends to increase, okay? In order to go from high entropy back to low entropy, that actually takes effort, okay? It doesn't just happen on its own, okay? So high entropy to low entropy, which would be a negative delta S, is not favored, whereas low entropy to high entropy is a positive delta S, and that is favored by the universe, okay? So like I said, reactions that decrease entropy are less likely to occur than ones in which entropy increases. The units of entropy are joules over Kelvin, so you might realize that the way that we calculate it is the energy over the temperature. That doesn't matter so much, just know that it's joules over Kelvin. So how do we predict changes in entropy? Sometimes we can just look at a chemical reaction and know if it's increasing or decreasing. So the first thing we would think about is entropy changes associated with changes in state. These are very easy to predict. So here's an example. Stop doing that. Water vaporizing. So water vaporizing is actually going from liquid to gas. So think about those molecules. They're going from liquid state in which they're, kind of held down by gravity, just sliding past each other, to a gas where they're free floating, moving at a much higher speed, going everywhere. That's an increase in disorder. So we can make that prediction. So delta S is positive in that case. Methanol melting, okay? So methanol is this chemical here. Again, if we go from solid, where the particles are locked into place, there's not a lot of disorder there, to a liquid, where they're actually free to move about, again, that is a positive delta S. The disorder, the chaos, the dispersion of the particles is increasing. So you can make the prediction based on the state or phase. The second possibility, or the second thing to think of, dissolving a gas in a solvent always results in a decrease in entropy. So here's an example. Carbon dioxide dissolved in soda. So we had carbon dioxide free floating in the gas state, and we dissolve it in water so it's more trapped. Okay, so over here the molecules were free. Over here we think of them as trapped in the liquid. That's going to be a negative delta S. Okay, that's going to be decreasing entropy. Okay, so again, that would be a negative delta S there, decrease in entropy. And that's not going to happen spontaneously. Carbon dioxide doesn't spontaneously become aqueous. Actually, the opposite is spontaneous. If you open a can of soda, we know that the carbon dioxide leaves. It becomes flat. So the dissolving is not favored. Another prediction that we can make, the dissolving of a solid into a solvent is always an increase. So again, sodium hydroxide dissolved in water. So again, think of it kind of like the state. We're going from a solid where they're trapped or locked into place to the aqueous state where they are floating, moving. That's more entropy, okay? So delta S, would it be positive or negative? It would be positive, okay? Randomness disorder is increasing. Another prediction we can make. The entropy of a system increases when the number of gas product moles is greater than the number of gas reactant moles. So if you have reactants becoming products, and let's say you have 2 moles of a gas over here, and it decomposes and it forms like 4 moles of a gas, okay? You're going from a few number of particles to more particles. So that's going to be an increase in disorder. It's like if you have a room with 3 cats in it and you put in 9 extra cats, that's going to be a lot of chaos, okay? So here's an example. Here's the chemical equation. We have 2 moles of a gas on the reactant side turning into 3 moles of a gas on the product side. So what would the delta S be, positive or negative? It's going to be positive because the randomness, the disorder, the chaos is increasing. Finally, an increase in the temperature of a substance is always accompanied by an increase in the random motion of its particles. Remember that the kinetic energy increases with temperature, so if you increase the temperature, the molecules are moving faster. So again, that's like if you have 3 sleeping cats in a room, and then they become 3 crazy awake playing cats in a room. That's going to be more entropy, okay? So let's do some quick practice on this. Predict the sign, positive or negative, and give a brief explanation. So you might want to pause the video here and try each of these. All right, let's go through each one. So this one, first thing I always check is the state. We have gas turning into gas, so the state isn't going to be the factor here. So instead, I have 2 moles of a gas on this side turning into 1 mole of a gas over here. So less gas particles is going to be a negative delta S, okay? Next, I check the states. I have a gas becoming aqueous, okay? Gas is free moving, aqueous is trapped in a liquid, so because there's less motion, there's less entropy, so that's negative delta S. Okay, this one's kind of tough. We haven't exactly talked about this yet, but I'll explain it now. Liquid methanol turning into aqueous, okay? What that means is that it dissolves in water, so I want you to think of it as mixing, okay? So think of it as taking 2 separate things, some methanol and some water, and then you mix them together. It's like you take your drawer of shirts and your drawer of pants and you mix them all together. That's going to be an increase in entropy, okay? Finally, our last one is going from solid to liquid. That's more motion. More motion is a positive delta S value. So there's all those answers there. How do we calculate this? So, of course, we're in chemistry. Chemistry is like a math class. We always want to calculate it. We're going to use that Big Mama equation that we learned earlier. It's sometimes called the summation equation, okay? You're going to use standard entropies from a data table. If you're in Ms. Hammer's PreAP class, this is a data table that you have at the front of your packet, okay? And our example problems are going to have the standard tables listed within the problem. So here's number 1, calculate the entropy change for this reaction. So delta S equals question mark. So it's products minus reactants just like before. So delta S, in this case we have 2 products, so it's going to be product plus product, and we have 1 reactant, we're going to subtract that one, okay? So everything has entropy. Notice, by the way, that the CO2 has the high entropy, really, really high. That's because it's a gas and the others are solid. That's just a useful thing to point out. So anyway, our delta S takes our first product. Well, our first product was the CaO, calcium oxide, and its value is 38.2. So we're going to take 38.2 plus CO2, so 213.74, minus the reactant, calcium carbonate, which is 91.7. So we're just going to grab our calculator and calculate this out. So 38.2, turn your calculator You're on, Miss Hammer. 3888.2 plus 213.74. Switch to this. Minus 91.7. So this is our answer, 159.5. I'll go back here, 159.5. 159.5. Remember, the unit here is joules per Kelvin. So that's your entropy change. Notice that it's a positive value, and that makes sense because we went from solid to solid and gas. So going from solid to having some gas, that's more disorder, more motion. It's an increase in entropy. So maybe I hit a wrong number. We'll fix that. Enthalpy versus entropy, which one matters more? So we've said that the following changes are favorable or spontaneous. Exothermic reactions, so negative delta H values are favorable. Okay, nature tends toward exothermic reactions. Increasing entropy, positive delta S, nature tends towards increasing disorder. Okay, well, what if some sort of chemical change is endothermic, which is a positive delta S, and has an increase in entropy, which is this is positive delta H, endothermic, and has an increase in entropy, positive delta S. So the increase in entropy is favored. The increase in enthalpy is not. Okay? So this is like two people having a disagreement. One says that a change should happen, one says that a change should not happen. How do we decide? Well, we have one more equation to learn. We have to talk about this thing called free energy. Gibbs free energy, abbreviated with a capital G, is the energy available to do work. It basically is a combined function of both things, entropy and enthalpy, and it is like the ultimate deciding factor as to whether a chemical reaction is going to occur or not. So the formula for it is the delta G, which is again the almighty determining factor for whether a reaction happens, equals delta H minus T delta S. So it takes into account delta H and delta S to determine whether it should happen or not. When delta G for a reaction is negative, the reaction is spontaneous. This is like the important thing to learn here, okay? If you solve this and delta G is negative, the reaction is going to happen. If you solve for it and delta G is positive, the reaction is not going to happen. So that's your like ultimate deciding factor. This is a useful thing to add into your notes. All units have to match, so I put everything in joules, okay? If you think about it, delta H is usually in kilojoules, and delta S is joules per Kelvin. Well, that's a mismatch. So you need to get rid of the kilo and change delta H to joules so that you can actually do the math. So here's an example problem for free energy. For a process, delta H is 145 kilojoules. Again, that's a positive delta H, that's not favored. And delta S is 322 joules per Kelvin. That's a positive delta S that is favored. So this is a situation where we have that disagreement. We don't know if the reaction is going to happen or not. So to figure out if it is spontaneous at a certain temperature, 382 Kelvin, there's our temperature, we have to solve for delta G. So delta G equals delta H minus T delta S. We want to put everything in joules. So kilo means 1,000. So our delta H is 145,000 joules. So that's the number I'm going to plug in. So 145,000 joules minus temperature times entropy change. So minus 382 Kelvin times 322 joules over Kelvin. So notice how the Kelvins cancel. That's how the units work. So we're going to again grab our calculator and do 145,000 minus, I'm going to do parentheses, 382 times 322, close parentheses. And our answer, it looks like it's going to have 3 sig figs. So 21,996. Rounding this off would be, let's say 22,000. Now, if we're going to get picky and want to have 3 sig figs, that's joules, I can put it into scientific notation. So 2.20 times 10 to the 4 joules. So the question though is the process spontaneous? So we think about the sign. We have a positive delta G. Is that spontaneous or not? It is not. So the answer here is no. The reaction is not spontaneous because delta G was positive. It doesn't matter the size of the number of delta G. It can be a big or a small positive number. As long as it's positive, the reaction doesn't happen. Okay, here's another one, and I'll do this one for you. It says, is the reaction of nitrogen gas and hydrogen gas producing ammonia gas spontaneous under standard conditions? Okay, you need to recall what standard conditions are. It means 1 atmosphere of pressure. That's kind of irrelevant in this case. And 298 Kelvin. Okay, so we're going to plug in our numbers. Again, delta H needs to be in joules, so we get rid of the kilo and multiply by 1,000. So negative 91,800 joules is my delta H. Delta S is a negative 197. So plugging in, delta G equals delta H minus T delta S. Negative 91,800 joules minus temperature, 298 is standard temperature for thermostuff, times negative 197. So let's grab our calculators, pause, and you do the calculation. Negative 91,800 minus, open parentheses, 298 times negative 197. We get negative, let's see, 3 sig figs, negative 33,100. So negative 33,100 joules. So that's your numerical answer for delta G, but what does it tell us? If delta G is negative, the answer is yes, the reaction is spontaneous. So that's why you solve for delta G, to answer the question, is it spontaneous? Okay, just a quick little summary of whether or not a reaction is going to happen, okay? These are just quick little questions that you could answer. This tells you the sign of delta S and delta H and the end result, if it's going to be spontaneous or not. So remember that a positive delta S and a negative delta H are both spontaneous. So if you have that combination, delta G is always going to be negative, okay? So it's always going to be spontaneous because they both agree. At the opposite end of the spectrum, if delta S is negative, that's not spontaneous. Delta H is positive, that is not spontaneous. The reaction's not going to happen. There's nothing driving the reaction. It's going to be positive delta G. Okay. Well, what about the combination of yes and no? Negative delta S is a no. Negative delta H is a yes. Is it going to happen or not? Well, it's only going to be spontaneous at relatively low temperatures. I'm not going to have you calculate what those temperatures might be. You just need to know that it's only sometimes spontaneous if they're both negative, and it's spontaneous at low. So I always remember negative, negative, low, okay? Well, what about if they're both positive? Positive delta S is spontaneous, positive delta H is not. So again, we have that disagreement. Well, this one's only spontaneous at high temperatures. So I remember if they're positive, positive, it's only spontaneous at high. So negative, negative, low temperatures, positive, positive, high temperatures. These are the ones that I guess you could say are the sometimes spontaneous. All right, that's it. So your homework is worksheet 4 in your packet, and that will be due tomorrow. Thanks for watching.